deep learning with TensorFlow. Now, if you like that little animation, that's just a taste of what to come, because we're going to have lots of fun learning deep learning with TensorFlow. Now, if you're here for that, you might be asking yourself the question, what is deep learning? Well, for these type of questions, and you'll probably notice this trend throughout the course. Oh, we've come to our friend Google here. What is deep learning? Oh, there we go. A type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract progressively higher level features from data. Whoa, there's a lot going on there. You might be thinking, Daniel, why did we go straight to Google at the beginning of this course? Well, for questions like this one, where there's some sort of definition, this is what I want you to do. If you're not sure what it is, I want you to search for it and do some research, because what we're going to be focused on in this course is getting hands-on as quick as possible. So we're going to be writing lots of code. So let's come into my definition of machine learning for this course. Machine learning is turning things, data, into numbers and finding patterns in those numbers. And you might be thinking again, now Daniel, I've signed up to this deep learning with TensorFlow course. Why have you got machine learning there? Well, we'll answer that question in a second. But in terms of finding patterns, how does this happen? Well, the computer does this part. How? Code and math. Now, we're going to be writing lots and lots of code to do this. More specifically, code or deep learning code with TensorFlow. So let's have a look at machine learning versus deep learning. We have this fun little diagram that you might also find on Google. There we go. Artificial intelligence. Artificial intelligence, machine learning, deep learning. There we go. Very similar one here. So if we have the broad field, that is artificial intelligence. So trying to get a computer to think for itself. And now if we have machine learning, which comes under artificial intelligence, remember the definition for machine learning from before was writing code for a computer to figure out patterns in data. Well, deep learning is usually considered a subfield of machine learning. And so this is about all you need to know for the time being. I mean, if you want to do your own research, what deep learning is, go ahead and do that. But again, with this course, we're going to be focused on getting hands-on writing deep learning code. So if we come here, what's the difference between traditional programming versus machine learning or deep learning programming? So with traditional programming, you might start with some inputs. You might code up a bunch of rules. In our case, we've got our favorite Sicilian grandmother's chicken dish here. And she's got this recipe and she knows it off by heart and she's passed it on to you because you want to host a dinner party at your place and invite everyone over. So you might start with the inputs, which are the ingredients. We've got some vegetables here. We've got the chicken, of course, and we've got the rules. This is what we have to do. Cut the vegetables, season the chicken, preheat the oven, cook the chicken for 30 minutes, add vegetables. And then if you've done all this correctly, you'll get this beautiful output. But where machine learning algorithms usually differ is that you'll start with the inputs and the ideal output. So this is the major difference here. We're going to be very familiar with this concept of inputs and outputs by the end of the course. And so what happens with a machine learning algorithm is you'll show it examples of what the inputs look like and what the ideal outputs look like. So this is a beautifully cooked chicken here from this input. So you'll start with this, and then the algorithm will figure out, hopefully, will figure out the ideal rules to get from this input to this output. All right. So now we've got a little conceptual overview of deep learning, very brief. The next question to answer is, why would we want to use machine learning or deep learning? So the good reason is, why not? I mean, you might have seen what machine learning is capable of. You might have heard of the power of deep learning, the power of artificial intelligence, and just all the problems we've got in the world. Why not we just use it? Maybe. But a better reason is, for a complex problem, such as maybe we're trying to teach a self-driving car to drive, can you think of all the rules you'd have to code if we remember back to our Sicilian grandmother's famous chicken recipe? maybe you can code up the rules for that, such as preheat the oven, cut up the vegetables, cook the chicken for 30 minutes. But in terms of self-driving car, when you go for a drive, do you think about the rules in your head, or do you just drive? You'd need stop signs, you'd need traffic lights, you'd need what to do for another car. You can imagine how that problem gets quite out of hand pretty quickly. So for a complex problem, can you think of all the rules? Probably not. And so I found this great comment on one of my YouTube videos here, the 2020 Machine Learning Roadmap. So be sure to check that out if you haven't checked it out. This is from 𝗖cie. I think you can use ML, so machine learning. If you see ML throughout this course, it's machine learning, for literally anything as long as you can convert it into numbers and program it to find patterns. Literally. It could be anything, any input or output. Oh, we've seen that again, input or output from the universe. Wow. Important piece to note here is as long as you can convert it into numbers. Now again, if you're reading this and you're like, Daniel, this doesn't make sense. I've never experienced deep learning before. Don't worry. We're going to have plenty of practice throughout the course. But here's the exciting part. I think you can use ML for literally anything as long as you can convert it into numbers. I want you to keep that sentence in your head. However, when should you not use machine learning? If you can build a simple rule-based system, or actually maybe not very simple if you're building a complex software product that doesn't require machine learning, do that. Where's this come from? Well, this is from a very wise software engineer. It's actually Rule 1 of Google's Machine Learning Handbook. So this is our first external resource for the course. There's going to be a bunch of these, so don't worry. I'll link them to wherever you need them. So this is the rules of machine learning. Best practices for ML engineering. We're not going to go through this, but I'm going to link to this. If you want to read through this in your own time, feel free to do so. This is a very exhaustive resource to get you up to scratch on how Google thinks about using machine learning. So we'll come back. So yeah, if you think about using machine learning, but you think you can code up a simple rule-based system, you should probably do the rule-based system rather than machine learning. So what is deep learning good for? Problems with long lists of rules. So when the traditional approach fails, machine learning/deep learning. Again, whenever you see throughout this course machine learning/deep learning, you can kind of think of them as the same thing. May help. Continually changing environments. So if the problem you're trying to solve is constantly changing, the information you're dealing with is continually changing. The good thing about deep learning is that it can adapt to new scenarios. So if the problem you're working on changes, you can train another deep learning model on those changes. Discovering insights within large collections of data. So imagine the problem of trying to take photos of food and identify what's in that photo. Can you imagine trying to handcraft the rules for 101? So you just wanted to start with, you were building an app called 101 dishes. So you've got maybe spaghetti, ramen, steak, eggs, kale, coffee. Can you imagine trying to handcraft the rules for what 101 different kinds of food look like? I can't. Now, what is deep learning not good for? Typically, again, take this with a grain of salt because as you'll see, as you get deeper into your, pardon the pun, deeper into your deep learning journey, you'll see there are lots of ways, if you're stuck on a certain problem about what we're about to see on this slide, you can kind of formulate ways to circumvent that problem. When you need explainability. So the patterns learned by a deep learning model, again, we haven't seen these, but we will get familiar with them, are typically uninterpretable by a human. So if a deep learning model is finding lots of patterns in numbers, which we'll see throughout this course, typically those patterns are quite hard to interpret once you look at them. When the traditional approach is a better option, remember, if you're going to accomplish what you need with a simple rule-based system, you should probably do that. When errors are unacceptable. So since the outputs of a deep learning model aren't always predictable, meaning they may contain errors, maybe deep learning isn't your best option. If you need a software system to do the same thing every single time, potentially a non-deep learning based system is what you're after. And when you don't have much data, so deep learning models usually require a fairly large amount of data to produce great results. However, we'll see how to get great results without huge amounts of data. So as I said, typically not good for. There are ways to kind of try and circumvent these points here. So let's have a look again. Machine learning versus deep learning. So in terms of when to use machine learning versus deep learning, traditional machine learning algorithms have typically performed best on structured data. So what I mean by structured data is data or information you can find in an Excel spreadsheet or a Google Sheets. So you've got rows and you've got columns. So this is clearly row 2, for example. We've got car sales, we've got a make, we've got a color, we've got odometer, doors, and we've got a price. So maybe we want to build a deep learning model or a machine learning model to take these parameters here, which are often referred to as features. So columns, features, make, color, odometer, doors, and predict the price. Whereas deep learning typically performs better on unstructured data, such as natural language text, or in the case of we wanted to build our Food 101 application to take photos of food and identify what's in that food, or if we have a Wikipedia article talking about deep learning. So this is example of data that you could argue that there is structure to this picture. Like, I mean, you got a shape here, you got shapes there, and here you've got a sentence there, but it's certainly nowhere near as structured as what you find in an Excel spreadsheet. And then again, you could have something like voice, so sound waves. If we go here, we'll dig a little deeper into the structured versus unstructured data. Let's have a look at some of the most common algorithms you're going to come across in the machine learning and deep learning world. Of course, this slide only goes through just the names of the algorithms, but we're going to be getting hands-on with building some of the most common deep learning algorithms you see coming up in a minute. So on the machine learning side of things, you might have the random forest, the naive Bayes, nearest neighbor, support vector machine, and many more. And since the advent of deep learning, these algorithms here are often referred to as shallow algorithms. Now, what that means for now is not too important. I just want you to start getting familiar with some of the terms you're going to hear in the machine learning and deep learning world. So when they come up, you're not going, wow, what does this mean? Now, on the deep learning side of things, we have neural networks, fully connected neural networks, convolutional neural networks, recurrent neural networks, and the transformer architecture is a fairly new one that's only come out in the last couple of years. And for this course, we're going to be focused on building these 4 type of neural networks here with TensorFlow. These are kind of like the bedrock type neural networks, the ones that a deep learning field over the past decade or so has been built on top of. And again, if we're looking at through the structured data versus unstructured data paradigm, these algorithms here, the machine learning algorithms, are typically better performing on structured data, whereas neural network type architectures are typically better performing on unstructured data. However, depending on how you represent your problem, many algorithms can be used for both structured data or unstructured data. All right, so in the last video, we heard that neural networks are a common deep learning algorithm. So what exactly are neural networks? So remember, for these type of what questions or definition questions, I want you to get really familiar with going in, what are neural networks? Explained, neural networks. Neural network, okay, Wikipedia. These are generally quite wordy definitions. A neural network is a network of circuit or neurons, or in a modern sense, an artificial neural network composed of artificial neurons or nodes. So you might get diagrams like this. And so that's just a one-sentence definition, but let's have a look of an overview of what neural networks are. So we might start with some data here, whether it be images of food, or some natural language text, or some sound waves, like what's going into the microphone here. And then if we want to use that data with a neural network, we're going to have to somehow turn this into numbers. So this is called a numerical encoding. There are many different names for it, but we're going to treat this as a numerical encoding. And you might be wondering, what are these square brackets? Well, that's to represent that we've got this data here and we've turned it into a numerical encoding, which is often referred to as a tensor, but we'll see that. We're getting ahead of ourselves here. And so before data gets used with a neural network, it needs to be turned into numbers. Okay, remember our one-sentence definition of machine learning. Machine learning algorithms are about turning data into numbers and finding patterns in those numbers. So this is our numbers here. Now we might feed these numbers here that represent our data into a neural network. If we come here, this is a simple neural network. This is a very similar diagram here, but probably a little bit more colorful. And what is this neural network going to do? Well, it's going to learn a representation, all the patterns, features, weights. These are other terms you might hear of what kind of representation it learns. And again, depending on what problem we're working on, whether it's recognizing images or discovering meaning from text or trying to turn a sound wave into text, you're going to have to choose the appropriate neural network for your problem. We'll see how to do that in upcoming lessons. So this is, okay, we've got 3 steps so far. We've got data as inputs. We've turned that data into numbers. We're going to feed that to our neural network, and this is going to learn a representation or find patterns in these numbers. What does it do then? Okay, then it's going to create some representation outputs. You might notice that these numbers have been transformed. And so this might not mean anything to us now. We're going to inspect this in a moment with TensorFlow code. But what these representation outputs are basically the neural network going, you know what, I've taken in these numbers here. I've found the patterns. These are the patterns that I've found in a numerical representation form. Okay, all right, and then what do we do next? Well, it's up to us to take these representation outputs that our neural network has learned about our data and convert them into human understandable outputs. So say, for example, in classifying image as food, we might have a photo of ramen here, might have to turn that into numbers in some way, might have to feed it through our neural network and get our neural network to discover patterns in that, so it outputs into a representation output. And then it's our job to write some code to convert these representation outputs to hopefully, if it's learned it right, it's going to output the label ramen. And the same goes for this photo of spaghetti. We could pass that through and it goes to there. And maybe for this tweet, we want to say we were building a system that was to read a tweet and say we wanted to know where natural disasters are going on in the world. Can we convert this tweet into numbers, feed it through a specific type of neural network, convert it into some sort of representation output, and then label it as, say, a disaster-based tweet or not a disaster? And then finally, say we're building a smart speaker or something to recognize sound waves. How would we turn those sound waves into numbers? Pass it through our neural network, get our neural network to discover patterns in those numbers, create a representation output, and then translate or transcribe, I think transcribe's a better word there, transcribe that to, hey Siri, what's the weather today? Whoa, there's a lot going on here. But again, this is the whole premise of neural networks here. We have some inputs. We turn those inputs into a numerical encoding. Our neural network that we've chosen for our specific problem will learn a representation referred to as patterns, features, or weights. We'll create some kind of representation output based on the patterns it's figured out. And then it's up to us to define what we want our outputs to look like based on this. So let's look at the anatomy of a neural network. So if we have it here, the first layer of a neural network is referred to as the input layer. So when you see diagrams like this is actually a very common diagram of what a neural network is. If we go here, neural network, back, what are neural networks? There we go. So we have inputs, something in the middle, outputs. Remember in our previous slide, our input, the data goes in here. In this case, this would be labeled with, these are 2 hidden neurons. Again, we're going to get very familiar with these terms as we keep going. And in the middle here, there's hidden layers. You'll notice this is a plural. So usually there's one input layer, or depending on what data you work with, you might have multiple input layers. Hidden layers, this can be an arbitrary amount of layers. So you could have one hidden layer, or you could have 152 hidden layers. So these hidden layers learn the patterns in the data. And then it has an output layer. So this outputs the learned representation or prediction probabilities. Again, we're going to get very hands-on with all of these terms. I don't want you to get too flustered with the terms that I'm putting out here because we're going to see all of these in action. And in this case, with the input layer, there's 2 neurons, and there's 3 hidden neurons here, and there's 1 neuron in the output layer. And I want to put a little tidbit here, is that when I say learns patterns in data, it's kind of an arbitrary term because you're going to hear lots and lots of jargon and different terms for different things in machine learning. And I'll try use as many different terms as possible, but also tie them back to kind of a single term. So when you hear me saying patterns, you'll often hear different things like embedding or weights or feature representation or feature vectors. And these are often all referring to very similar things. Now, when it comes to neural networks, we've seen the anatomy, but there's also a few different types of learning. The first one is supervised learning, semi-supervised learning, and then unsupervised learning, and transfer learning. Whoa. And so supervised learning often involves having data and labels. So in the case of identifying different images of food, we may have the data would be the images of the food, and the labels would be the labels of food. So ramen, spaghetti, coffee, steak, pizza, associated with each one of those images. Semi-supervised learning has some data, or actually could be as much data as supervised learning, but it only has some labels. So for example, maybe we had 10,000 images of food, and we only had labels for 1,000 of those images. And we wanted to train a neural network on the images which have labels. And then we use that neural network to try and label the other images of food, the ones we don't have labels for. And then unsupervised learning is you basically only have data and no labels. You kind of pass your data to a machine learning model or a neural network or a deep learning model. Again, very similar terms for very similar concepts. And you kind of go, hey, I'm not sure what patterns are going to be within this data, but see what you can find anyway. And then transfer learning, which is actually a very, very important concept. We're definitely going to get hands-on with this one. The beautiful thing about deep learning models is when they learn patterns in some sort of data set, those patterns can be used for another problem type. So transfer learning would be taking what one deep learning model has learned on some set of data and then using it in another problem on another set of data. So in our food image discovery or image classification problem, we may take what a machine learning model has learned on just pictures of the world, so general pictures, and apply that to our specific images of food. Now, in terms of this course, we're going to be writing lots of code to do supervised learning and transfer learning. But again, the premise of what we're doing, starting with inputs, turning that into numbers, and then having some sort of algorithm go through those numbers, find patterns, create outputs, can also be used for these other two types of learning here. Now, what is deep learning actually used for? Well, we'll return back to this comment we saw before, because this is actually a beautiful comment. Thank you very much, 𝗖cie. Hopefully I'm saying that right. I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. Literally, it could be anything, any input or output. Again, lots of emphasis on input or output from the universe. And so I want you to keep this sentence in your mind, because by the time you finish this course, you're going to look at the world through a different lens. I mean, you're going to walk down the street and you're going to wonder, how could I represent this experience that I'm having in numbers and then program a machine learning algorithm or a deep learning algorithm to find patterns in those numbers? Seriously, once you learn the concept of machine learning and deep learning, you start to look at almost everything through the lens of turning something into numbers and finding patterns in those numbers. Now, let's have a look at some common deep learning use cases that you've probably experienced in your day-to-day life. So the first one is recommendation, translation, speech recognition, computer vision, natural language processing. Again, emphasis on some here because there's many more, but these are some of the main ones. So the recommendation here is my YouTube home screen. We've got some programming videos. We've got a video of my friend's YouTube channel, an interview from Peter Norvig, one of the heroes of artificial intelligence, some RuneScape videos because that was a game I love to play, jiu-jitsu, some bodybuilding. Oh my goodness, more hacking videos. So I can safely say YouTube has learned me pretty well. And now this is based off, again, my history of the things I've watched on YouTube. And so if YouTube has all of that information, it can go, you know what, Daniel, I've seen 100 different people, or maybe in the case of YouTube, there's actually close to, I think, over 1 billion users on YouTube. Maybe there's 100,000 people out there like me. And they're like, you know what, you've watched programming videos, so we're going to show you this one. And you're interested in the movie Her, great movie, by the way. We're going to show you this soundtrack based on the patterns that we found in everyone else's YouTube browsing history. And then in the case of translation, we might have some language here. This is English, the language that I speak. And if I wanted to speak Spanish, I'm not even going to pretend that I can pronounce that. I can type in my sentence here, deep learning is epic. And then Google will run a deep learning algorithm to figure out the patterns in this English sentence and translate that into Spanish. So if you're a Spanish speaker out there, you can tell me or send me a message of how accurate this translation actually is. In the case of speech recognition, we may have some sound waves, again, like what I'm saying here. And when I find out from Siri, it's like, hey, who's the biggest big dog of them all? And so deep learning probably go through that sound wave and transcribe it into this sentence here. Computer vision, actually, this image is a bit painful for me because this is actually from some security footage from one of my neighbors. You see this car here? If I had a computer vision algorithm that was running on this security camera, maybe I could pick up this car or found the license plate because this car, actually, the trailer, it had a trailer on the back. The trailer came off as it was driving past my car on the street, and the trailer hit my car and basically totaled the whole car. So now I need to find a new car. And this was the car that did it. So if their security footage had a computer vision algorithm, maybe we could have found it. So I'm still on the investigation for that, but that's one use case computer vision can be used for. So again, a deep learning algorithm may take the pixels of this image, find the patterns and go, you know what? I've seen a car that looks like this before. Maybe it's a Toyota Hilux that you're looking for. Anyway, we'll leave that problem there before I get too upset. I really loved my car. And the other one is natural language processing. So maybe taking in an email, you got your text here. So unstructured text here. Hey, Daniel, this deep learning course is incredible. Oh, thank you so much. I can't wait to use what I've learned. I hope you send me a lot of these type of emails here. That is my actual email address, so feel free to send me whatever you want. And this is not spam, so this is something I want to see in my inbox. But if you're sending me messages like, hey, Daniel, congratulations, you win, that is a big number. I'm not going to pretend that I can read that out loud without slowly deducing how many zeros there are. That's spam, so I don't want this in my inbox. I want a natural language processing algorithm, a deep learning algorithm, to put that in my spam box. And so if we dive a bit deeper, you might see these referred to as sequence-to-sequence, or sec-to-sec for short, deep learning problems. Now, the premise here is if sequence-to-sequence doesn't make much sense, just think about it like this. You have a sequence of words and you want to translate or transform that into another sequence. That's what you're trying to doing with seek-to-seek problems. Same with here. You might have a sequence of sound waves and you're trying to convert them into another sequence of words. And for this problem here, it's called classification or regression. Now, classification, is this email not spam or spam? Is it one thing or another? There's also multi-class classification, but we'll get onto that in a second. And then regression, you might be wondering, hey, Daniel, I've heard regression is more so for predicting a number. Yes, well, in this case, in our computer vision problem, our numbers might be the pixel coordinates of where the corner of this box should be. So maybe we start with an image that doesn't have a box on here, and then our computer vision algorithm looks over it, or our object detection algorithm looks over it, and goes, you know what? I think the car is most likely in the box here. So maybe that's 50 pixels in from the x-axis and 60 pixels down from the y-axis there. And so that's that corner, and then it does the same for each other corner. Now, I want to show you another phenomenal use case for deep learning that only just recently happened. So if we go here, now you could also just go deep learning use cases, and you're going to get a whole bunch of different ones. There we go, automatic speech recognition, image recognition, natural language processing. But there's one I'm specifically looking for. Now this is DeepMind. Deep stands for deep learning. Now this is a deep learning research company. Boom, AlphaFold, a solution to a 50-year-old grand challenge in biology. I'm not going to go too much into this, but this is possibly one of the biggest breakthroughs in AI powered by deep learning, as well as, oh, do I want cookies? Fine, I'll have the cookies, as long as they're delicious. Now, do we have deep learning here? Here we go. Now, new deep learning architectures we've developed have driven changes in our methods for 𝗧𝗯𝗹𝗲, enabling us to achieve unparalleled levels of accuracy. Again, I'm not going to go too deep into this, but this is the type of, I believe they've used a deep learning algorithm. This is actually brand new, to figure out how a protein should fold. Now again, I haven't read up on the research here, but this is just the type of things that deep learning can be used for. If you remember the comment we looked at before, the YouTube comment, I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. So that's what DeepMind have done. They've taken proteins, turned them into some sort of numerical representation, crafted a deep learning architecture to find patterns in those proteins. So this just blows my mind. As I said, by the time you finish this course, you're going to have a new lens on the world. So we've seen what deep learning can be used for. How can we write these deep learning algorithms? So this is where TensorFlow, that's worthy of seeing again, TensorFlow comes in. So in the next video, let's figure out what TensorFlow is.